Okay, let's go to problem 7. By the way, what's the multiplicative identity? What's the additive identity? What does it mean? 0, because you add it, nothing changes. How about the multiplicative identity? 1. Multiplicative inverse? Yes. When you multiply it by the thing, you get 1, right? Okay, good. So you have a complex number here for problem 7. We're still in worksheet 15, right? Problem 7 now. You have the complex, so part 1. You have this complex number z is e to the I theta. And the question is, what is the multiplicative inverse? So meaning, with what should I multiply z to get 1? So first I need to get rid of the exponent, right? I need to make it 0. So I need to multiply by e to what power? Yeah, e to the what? I theta. And then how do I get rid of the absolute value of z? 1 over the absolute value of z. Yeah. So now these two, when you multiply them, what do you get? When you multiply 1 over z times z, you get 1. So which option is correct? I think you would say, oh, I see a typo. I mean, it's C, right? C. So in my solution, I have I need to just update something. So the C is correct, but I just typo. I'm catching all those typos and making it right. Okay. So part 2. Part 2. You got the number z here. It's 1 over v over r plus I omega, and v, r, omega, l are just real numbers. And then it says here, express z in terms of this Euler's formula. So in other words, here is z is equal to v over r plus I omega times l, right? And we want to write it as something e to the something, e to the I something. So first, you have the I on the bottom. What do you do? We did it earlier. Multiply numerator and denominator by the complex quantity. Thank you. So multiply, so by r minus I omega l, and then r minus I omega l, right? You can do this again because this is just 1, multiplying by 1. And multiplying by 1 doesn't change it. So once you do that, you will get z is equal to, these when you multiply them, you will get, first of all, in the numerator you get v, and then r minus I omega l, and then in the denominator you get what? R squared plus omega squared l squared, right? Yes. And this is equal to v times r over r squared plus omega squared l squared plus I, or actually minus I times omega lv, or v omega l, v omega l over r squared plus omega squared l squared, like so. So what did I do now? What benefit did this give me?
Separates the real.
Yes, I have my real, I have my complex. Now my goal is to write z as this. I want, so for this, I want to do this. I want to write z as some z, like some absolute value, and then e to the I theta. So So first, I need to find the magnitude of z. So, how do you get the magnitude of z? Square the x, or square the real part, square the complex part, and then take the square root, right? Okay. So first of all, they both have this in common, so you can just pull it out. The denominator is in common, right? So the absolute value of z becomes this. Becomes v squared r squared plus v squared omega L omega squared L squared square root over r squared plus omega squared L squared. How did I do this? How did, how was this possible? How did I do it?
You took the real part and the imaginary part,
Yeah.
you put them into the
Yeah,
x squared plus y squared.
good. Yeah, and then since this is in common, you're going to square it, factor it, and then take the square root, so you should get the same thing on the bottom. So that's why it looks like that. Now, if you like, the v squared is also common, right? You can factor v squared and take its square root, right? So you got z equal to v over, or v times this, r squared plus v squared, omega, we factored the v, right? Omega squared L squared divided by r squared plus omega squared L squared. Is this good enough, or I can maybe simplify a little more? What is this over this? This part is like the square root squared, right? So you can cancel one of the square roots and you end up with z equals to v over r squared plus omega squared L squared squared. Okay? So that's the magnitude of z. And of course the angle is, the angle theta is tangent inverse of what? Oh. This over this, right? The y part over the x part. The imaginary part over the real part. So when you divide them, both of them have the same denominator, so the denominators cancel, right, when you divide them. So you end up with just negative v omega L divided by VR. So it would be negative v omega L divided by VR. But you can cancel v. So you just end up with tangent inverse of minus omega L divided by R. Okay. So problem 7 is done. Number 8. So let me just summarize here for problem 8. Here's what's given. Here is the given. Z1 is equal to A e to the I alpha. Z2 is equal to B e to the I beta. And suppose Z3 is equal to C e to the I theta, so that Z1 is equal to Z2 times Z3, right? Z1 is equal to Z2 times Z3. So the question is find C and theta. Find C and theta. Well, plug them in and see what you get. So what do we do? Plug it in, right? Well, what is Z1? Z1 is A e to the I alpha. A e to the I alpha. And then Z2 is B e to the I beta. And then Z3 is C e to the I theta. So I want C and theta. So multiply by the inverse of this, or divide by this number here. So let's see. So you got this. C e to the I theta will equal to A e to the I alpha divided by E to the I beta. And so this becomes A over B e to the I what?
Alpha minus beta.
Alpha minus beta. Thank you. Beta, because the e to the I beta on the bottom becomes e to the negative I beta on top. Exponentials, they just add. So that means comparing them, right? The A over B is the modulus. So C is A over B, and theta is equal to what?
Alpha minus beta.
Alpha minus beta. Yeah. Okay. That was part one, right? Of product A. Okay, so part two. If Z is equal to minus I over omega C, right?
Yeah.
Okay. If Z is equal to I, negative I over omega C, we want to write Z how can I write Z in this format? So first of all, what's the magnitude of Z? What's the magnitude of Z?
Just 1 over omega c.
Just 1 over omega C, yeah. I mean, you square it doesn't have the real part, so the real part is 0. So when you square and then take the square root, you just get 1 over omega C, right? Got 1 over omega C. So this part is 1 over omega C. How about the other part? E to the I what?
Is this
I what?
Oh, so it would be 0. Oh, it's under.
Yeah, I like that. So what's that angle? Pi over 2, but negative. Negative pi over 2. So minus pi over 2. Here is y.
Oh, because it's infinite.
You have this, right? Just graph it. Where is the y-axis is this, right? Pi. And then negative, and then omega c. So negative is somewhere here, and omega c, something along this. So it's minus pi over 2. Okay, cool. So there is that. Let me make sure I have it. 1 over omega c e to the minus. Yeah, that's correct. Okay. Part 3. Oh, I need to move the angle of the camera. So here is, for part 3, here is the question. Part 3. Suppose you have this. V is V0 e to the I omega t, right? And then you're given this other one, I is equal to I0 e to the I omega t minus theta. Omega t minus theta, yes. And we're also given Z is equal to minus I over omega c. So we're given all this stuff. Okay? So now they say, suppose this. So if V is equal to Zi or Iz, if V is equal to Iz, find I0, this I0, yeah, I0 and theta. Find I0 and theta in terms of omega and C and V0. C, V0, and omega. That's the solution. Oh, just write it down and then see what you get. So here's what we're going to write. Let's write down V first. V is what? V0 e to the I omega t. That's the V part. So V0 e to the I omega t. Okay, let's write down now I. What is I? I0 e to what part?
I omega t minus
E to
theta.
the, yep, I omega t. In fact, this part, let me write it, let me expand it here and show you what it is. Because you will see in a moment why I'm doing that. This part can be written like this: I0 e to the I omega t, and then times e to the minus I theta. Do you agree with that?
And you can put that in the denominator.
Yeah, because yeah, these two can just be added, right? You have e to the I omega t minus I theta, and you factor the I. Do you agree that this is the same as that? Okay, we're good? Okay, because I want to write it this way for a reason that will be clear in a second. So this is e to the minus I theta. That's why I'm writing it. So this part is the I. How about the Z? The Z. Is it acceptable that I write it as just I, or should I, since everything is involved in exponential, should I write Z also something exponential?
We should also write it
In the exponential form. Have we done this before?
part two.
Yes, we have. We did it in part 2. Here it is. So the Z, this negative I over omega C can be written as 1 over omega C e to the minus I pi over 2. So let's do that. Let's plug that in. So here it is. 1 over omega C e to the minus I pi over 2. Yes. Okay, why am I doing this? Here's why. Well, first of all, you got e to the I omega t here and e to the I omega t here. They cancel. So that goes away. My goal is to solve for I0. So let me multiply. See, I have 1 over omega c here. I'll multiply both sides by omega c. So when I multiply by omega c, I will get V0 omega c is equal to. So on the right hand side, I will end up with the I0 e to the what? How do I combine these two? E to the negative I what?
So pi over 2 minus I theta?
Minus or plus?
Plus.
I'm factoring the minus sign.
Oh.
So it will be theta plus pi over 2 or pi over 2 plus theta, right?
Yeah.
Okay. Now, okay. Let's think about the following. The left side, is it positive, negative, real, complex? What is it?
Real.
It's real and positive. Because this is the modulus and all of these are just positive numbers. Okay, good. So that means this is positive and real. So the right side has to also be positive and real. Okay, positive and real. So to make it real and positive, I need this to be what? Theta plus pi over 2 to be what?
0.
To be 0. Yeah, to to be 0. Because it's e to the 0 is what? 1. So I need this theta plus pi over 2 to be 0. So that means theta is what?
Negative pi over
Minus pi over 2. Yes. So that means theta would be minus pi over 2. Do you follow the logic? This side is positive and real. I0 is the modulus of I, so it's also a positive real number. So everything is positive and real, so this has to go away. Anything complex needs to go away. Remember, complex is like cosine theta plus I sine. So if the sine is 0 if you got 0 or pi. I don't want to choose the pi because pi will give me negative number, because cosine of pi is negative 1. So I want the 0. So that means theta has to be negative pi over 2. So if that's that, then we're done. This part goes away, and theta will make it happen if it's negative pi over 2. How about the I0 part? If that's the case, what's I0 then?
E naught omega c.
Yeah, V naught omega c times V naught, or V naught omega c. Okay. For part 3. Yes. Okay, so we're there, and now it says you have I, you got your theta, and you have your I0. So find the real part of I. So here's I. Here is I. This is I, right? We want to find its real part. So let me write. So I is equal to I0. But what's I0 now? What did we say I0 is?
WC V naught.
Omega c V naught e to the I omega t minus theta. But what's theta? Negative pi over 2, right? But so minus minus becomes what?
Plus.
So plus pi over 2. Now, they want me to do this at t equals to 0 or what? No, not at t equal, at any time. So, okay, so the real part of I will be just omega c v0 times the cosine of omega t plus pi over 2. Yeah. The imaginary part will be plus I, and then omega c v0 sine. All right. Okay. Okay, moving on to the next one. Anybody bored from this? No, good. And you should be enjoying it. It's good stuff. Yeah. So, problem 9, you got, consider a real number A. So A is a real number. And you have a complex number Z. And Z can be expressed in Euler's, using Euler's formula as follows. In fact, I'm going to erase the board before I start, because I see multiple parts and I want to do it on one side. So let's do that. So for problem 9, still worksheet 15. So it says here, suppose A is real. A is real. Right? It's a real number. Z is this complex number, e to the I theta. So it's saying this, find, so for part 1, suppose, I want to find this, A times the real part of Z. What do I get? What's the real part of Z? A times what? What's the real part of Z? If Z is this. Z, absolute value of Z times what?
Just C naught.
times what?
To the power zero.
Let me
Okay,
expand this
oh,
one.
cosine theta, oh.
Yes, yeah, it's written this, you can write it this way, right? Absolute value of z cosine theta plus I absolute value of z sine theta, right? Yeah, so the real part of z is what? Absolute value of z times cosine, right? So it's the absolute value of z times the cosine of theta. Okay? How about this now? How about if I do this? The real part of a times z, is that the same? Well, first multiply z by a. If you multiply z by a, what do you get? You get a times the absolute value of z e to the I theta. And so what's the real part of that? Would be a times the real part times z times the cosine theta, right? So it's equal to a times z times the cosine of theta. So they're equal, right? That's all what this one is trying to show. And the same thing if you do the imaginary, right? If I do the a times the imaginary part of z, that would be part 2. That's right. Right here. The a times the imaginary part of z. So you got a. What's the imaginary part of z?
Is the sine.
Z sine. Absolute value of z times the sine of theta. And then if I want to do the imaginary part of a first times z and then do the imaginary, does it matter? No, it would still be. Okay. Part 1, part 2. Okay. So now, suppose z is a function of time, right? Now, so theta is omega t. And therefore, we have this. So now for part 3, here is part 3. Suppose z is equal to z absolute value e to the I omega t, right? E to the I omega t. E to the I. Yeah. So what we want to do, take the derivative of z and then express it in terms of Euler's formula. Okay? So we want to take the derivative of z and then express it in terms of Euler's formula. What does that mean? Let me write it this way. So first of all, dz dt. What do you get? What's dz dt?
I W T times Z.
Yep, you get I omega, and then the absolute value of z e to the I omega t, right? The I omega comes from the chain rule. So is this written in terms of Euler's formula?
Yeah.
You heard yes, and you heard no? Why not? For Euler's formula, you need what?
You need it in cosine.
What's in front should be real, and then e to something I. So is this real, what's in front? It's not, because there is this I here. So that I spoils, well, it doesn't spoil, but it's there, so we need to work a little more. So we need to write the I in terms of Euler's formula first, and then change it. So here's how it goes. So you got the omega and the z, those are fine, those are real numbers. How about I? What can I say about I? It's e to what?
To the square root of negative 1.
It's the square root of negative 1, but I want to write it as e to something. What's the magnitude of I? 1,
Oh, one.
right?
Oh, yeah.
The magnitude of I is 1. And what's theta for I?
Pi over
On the y-axis, yeah, the positive pi over 2. So I can be represented as e to the I pi over 2,
two. Oh.
right? Because think about it, e to the I pi over 2. You can write it as cosine of pi over 2. What's cosine of pi over 2?
0.
0. And then plus I times the sine of pi over 2. What's the sine of pi over 2? 1. So you get just I. So this works out. Yeah, that is it. And then don't forget the e to the I omega t, e to the I omega t. So dz dt, in other words, would be omega z e to the I omega t plus pi over 2. Okay? So, that's what we got. This makes sense, actually. It does. Because, remember, e to the I is like, you got sines and cosines. What's the derivative of a sine? The cosine. And what's the difference between a sine and a cosine? They're just shifted by what? A pi over 2. That's where the pi over 2 comes from. You must.
So for this problem, the magnitude of z and z naught are the same thing, right?
I'm sorry?
The magnitude of z and z naught are the same thing, right? As in the problem they write it as z naught.
And the problem it's written as z naught?
They mean the same thing, right?
Oh, yeah, okay. So I wrote absolute value of z.
Right.
And they're saying, okay, yeah, so yes, I meant,
Okay,
I should have paid more attention. Yeah.
that makes sense.
Yeah, so in the worksheet, they write z naught instead of the absolute value of z. Sorry about that. So maybe I should correct it. So you would write omega z naught e to the I omega t plus pi. This is better, right? Okay. Now they say, what's the real part and imaginary part? I think for part 4, part 4, this is 3, 4. Real part of dz dt is
Omega z naught. Cosine.
omega z naught. Cosine.
Omega t.
Omega t.
Omega t. Pi over 2. Thank you. And then the imaginary part of dz dt is omega z naught
Sine.
sine t plus pi over 2. Then one plate and imagine, yeah. All right. So now, for part 5, we would like to, here's part 5. Part 5. Let's go back to z itself. Here is z. Maybe I should write it as z naught something. Z naught e to the I omega t, right? So let's first find the real part of z, take its derivative, and see what we get. So here it is. Real part of z is what?
Z naught. Omega.
It's, yeah, z naught cosine omega t, right? Yeah? Z naught cosine of omega t. Next, we're going to take the derivative of that with respect to t. So d dt of the real part of z. You get d dt. What's the real part of z again? This, right? The real part of z is this. So, omega. Yeah, so you get z naught cosine omega t. I think I heard Subrat, he said already to derivative would be negative omega z naught sine of omega t, right?
Yes.
Okay. But the sine, what is negative sine?
Cosine plus
cosine plus, yeah, if I shift the cosine backward by pi over 2, I get negative sign. So it looks, so this is the same as omega z naught times the cosine of omega t plus pi over 2. Well, exactly the same as this one, right? Yeah, exactly the same as this one. So what this is saying is this: you can take the real part of z, just work with the real, right? Just keep your potential, your AC voltage real, plug it into the differential equation. When you take derivatives and so on, you'll get that. Or plug in the complexified part, like e to the I something, and then do everything, and then take the real part at the end, you will get the same thing. And then the same thing for the complex part, or the imaginary part. Imaginary part of z is z0 times the sine of omega t, right? And so d dt of the imaginary part of z is d dt of z0 times the sine of omega t. Derivative of sine is cosine, so you get omega z0 times the cosine of omega t. But this is the same as omega z0 sine of omega t plus pi, because sine looks like this. So if I shift it backward by pi over 2, I get cosine. Yeah, good stuff. That's part 5. So we're done with problem 9.
So the negative omega, so then you said, for the top part, yeah. So the pi over 2 makes it a sine.
When you add a pi over 2 to the cosine, you get negative sign.
Would it be positive sign?
No, because I always remember it this way. Here's cosine, right?
Yeah.
So adding a pi over 2 is like shifting it back, right?
Left.
Yeah. So it's like it starts
Yeah.
here now.
Okay, so then it becomes negative. Okay.
Yeah, negative sign. Yeah. Okay. Let's see if we can do one more. And I guess we will, yeah, just problem 10. For problem 10, I'm going to use that board because yeah. Let's go to problem, which one are we on? The 10, right?
Yes.
Yeah. So now we're ready to look at circuits, right? With the AC current after all this stuff. So it says in this exercise you will relate V, Vt, and I of t with the complex